In this film, I'm going to be making the Raspberry Pi Pico controller for my flashing level crossing lights, following on from part 1 of the project, the scratch building of the signs themselves, complete with the installation and wiring of the tiny LEDs, which we now need to program to flash in the right places. You can see that video in the link above, but you can also use my controller for off-the-shelf signs, so you don't have to make your own. But whichever way you go with the signs, my controller is cheap and relatively simple, both to build and code, even if you have little or next to no experience, and best of all, flexible, being easy to recode for different inputs, and for adding other features like sound, or even controlling servos to open the gates or lift the crossing barriers. But for now, we're going to stick with the lights, and I'll be taking you through the simple build, the easy to understand code, and finally finding a home on my layout, with power for the Pico taken directly from the track. My Raspberry Pi Pico is an inexpensive microcontroller, perfectly suited for this kind of thing. And don't worry if you've never come across one before, as I'll be demonstrating exactly what to do with it, including some entry-level programming. But first of all, let's set up the circuit, pushing the legs into a prototyping breadboard, onto which we're going to add the other components, the rows and columns, providing electrical connections under the grid of holes. Eventually, we'll be wiring in our crossing signs, but while we get everything set up, I'm going to use some standard LEDs, 2 red and 1 orange, even though it looks clear from the outside. And like most LEDs, we've got a long leg for the positive, the anode, and a shorter negative cathode. And we're going to plug them into the holes in the breadboard, the shorter cathodes in the row along the edge of the board, and the longer ones into 3 adjacent columns, the 2 reds either side of the amber, just as they would be on the sign. Under the board, the row of holes along the side are all joined together, so our 3 cathodes are connected, and now we want to link them to one of the several negative ground pins on the Pico, the ones with the square tops, completing one half of the circuit. Now we come to the positive side of things, wiring up to 3 outputs on the Pico. But first we're going to need some resistors to stop the LEDs blowing, 1 for each, just bridging the gap over the centre of the board. At the moment the resistances are quite arbitrary, just to protect the LEDs while testing. We'll come up with some final values later on, to optimise the brightness of our finished signs. So what have we got so far? We've got all 3 cathodes connected to one of the ground pins on the Pico, and a resistor for each anode, ready to connect to 3 positive outputs, which will supply 3 volts to the LEDs when triggered by the program. The Pico has lots of pins to choose from, and I've just picked 3 in a row, connecting each to the resistors with a short jumper cable. We'll come to identifying which is which a bit later on, but for now that's the wiring done, so time to set up the Pico. And for this we're going to need a host computer. I'll be using my Raspberry Pi, but a PC, laptop or Mac can be used in exactly the same way. Unlike a regular computer, the Pico doesn't have an operating system itself, so needs to be programmed externally. And first of all, set up with some firmware, installed by plugging it in with the boot cell button pressed. This only has to be done the first time you use it, and rather than going through the process in any detail here, let me provide a link to another film I made for a quick and easy setup guide, suitable for the not so technical minded. All the files are on the Raspberry Pi website, which has a good explanation of how to do it as well, and I've also added a link to that in the description. Once installed, the one thing that takes a bit of getting used to is how to access the files, as the Pico doesn't appear on the desktop as you would expect. Instead, we have to go through something like Thonny, which comes pre-installed on the Raspberry Pi, and it's here that we're going to do the programming for the Pico. When we open Thonny, we can see our Pico in the Files pane on the left, underneath the host computer, and it's here we want to save our as yet unwritten code, giving it a suitable name, with .py at the end as it's in Python, our programming language. The code is actually really straightforward, so I am going to run through the whole thing, starting by loading up some stuff from the MicroPython libraries, which is where the modules we need are. For the functioning of the hardware, we need pin from the machine library, and from utime, sleep. Utime being specific to MicroPython, which is on our Pico. Then we need to tell our program which pin to use for each of our LEDs, in our case 19, 20 and 21. And these are going to be output pins, so after the number we need to put pin.out. Then the same for the central amber, and that's in pin 20, working backwards from right to left along the side of the Pico. Once again, the Raspberry Pi website has all the information for which pin is which. Then it's on to the right-hand red, following exactly the same structure to the other 2, making sure all the parentheses and punctuation are the same, as it does matter which is a comma and which a full stop, and what's in capitals and what isn't. Now we've defined what's connected to what, we can get on with the program proper, which starts an infinite loop with while true, followed by an all-important colon. And then we want to assign a value to each of the LEDs, 1 for on and 0 for off. Both of our red LEDs starting unlit, with just the amber on at the start of the sequence, so that has a value of 1. And we want it to stay like that, so I'm going to get my program to pause for 3 seconds using a sleep instruction before going on to the next line of code, which is to turn the amber light off, giving it a new value of 0. At the same time, we want both of our red lights to come on, just for a short time, before the flashing wig-wag sequence starts in earnest, so each need a value of 1. Then once again we want to pause, sleeping the program for 0.75 seconds, an estimate of the timing for now. Now we want to blink the LEDs, left, right, left, right. The amber stays out, so we can leave that well alone. And I'm giving the left LED a value of 1, and the right one 0, so that now goes out. And we want it to stay like that for the same amount of time, sleeping the program for 0.75 seconds. This doesn't mean it's not doing anything, it's just not doing anything new. Then we want to switch it round, left LED off and right LED on. And in order to get that to repeat, I'm copying that chunk of code and pasting it as a duplicate afterwards. Now let's try out what we've got so far by running the program. First of all, our amber light comes on for 3 seconds, then the two reds together, before flashing alternately. This happens a couple of times before the whole thing starts again, the program looping back to the beginning. So far so good, but it's not exactly what we want, which is after the initial sequence, we want the wig-wag to continue indefinitely. So for this, I'm setting up another infinite loop inside the first one, using the same instructions, but indenting each line, just by 4 spaces, which means they only apply to this loop, and when the program gets to the end, it'll start this bit again, and not go right back to the beginning, so we can scrub that repeat, as the infinite loop will do that job. And when we run the program this time, we get the initial sequence of the amber and the 2 reds, followed by the flashing wig-wag, which continues indefinitely, that bit of the code looping back on itself. Now this is all very well when we've got our host computer to start and stop the program, but we need our Pico controller to stand alone. So now we're going to add some buttons, which will manually initiate the lighting sequence on the approach of a train, and stop it when the train has passed. It's also possible to automate these, being triggered by the passing train itself, but that'll have to wait for another film. So for now, we're going to stick with buttons, or more accurately, tactile switches. Like most others, mine have 4 legs, but these are actually 2 pairs, connected together on each side of the switch, and we're going to use the diagonally opposite ones, one for the input pin on the Pico, and the other connected to the 3-volt output, via the outer row on this side of the board. So when the button's pressed, it'll register as an input, and trigger an event in our code. If I had a bigger breadboard, I could push in all 4 legs into different connectors, but with space at a premium, I'm going to snip off 2 of the legs, the remaining 2 being on the diagonal, so we know they'll only be connected when the button's pressed. And with a blob of white tack to hold the button steady, I can push it into the breadboard, one leg beside the input pin on the Pico, and the other on the outer rail. My white button is going to start the lighting sequence, so I now need a black one to stop it, preparing the button in exactly the same way, leaving just the connectors on the diagonal, pushing one in next door to another of the pins on the Pico, the other into the outer row, which is then connected to the 3-volt output, supplying both of the buttons. Before we go on to coding them, let's have a quick reminder of what's connected to what. My LEDs are using pins 19, 20 and 21 as outputs, with my white button connected to GP22 and the black to 27, both as inputs, and it's with those numbers we can add the buttons to the program. As with the LEDs, we need to define the buttons with the pin numbers, giving them a suitable name, followed by a similar bit of code. But instead of pin out, these are inputs, so unsurprisingly need to be pin in. But as inputs we need another bit of code, which basically tells the button what to do when nothing's happening, ensuring its logic state is 0. You don't really need to know the ins and outs of this, just add it to the code. Then we can adapt that line for the stop button, using pin 27. Now we need to add the code for the button to initiate the light sequence, adding an if statement. So if the value of the button changes, which it will if it's pressed, even momentarily, the program will go on to the next line. But in order for that to be conditional on the if, absolutely everything has to be indented, and the lines for our nested infinite loop indented twice. But now we need to add some preconditions for what happens if the button isn't pressed, which is that each of our LEDs will be off. So I'm just copying a few of our lines and pasting before the if ensuring they share the same indent, and setting all the values to 0. So even though the program is already running, the light sequence itself will only start when the button's pressed. This will be vital when the Pico is powered by itself, away from the host computer, as we're not starting and stopping the program. That'll actually be running all the time. The button just starts the light sequence, which we now have to find a way of stopping. This we're going to do in the wig-wag loop, basically checking to see if the black button's been pressed each time round, where its value would be equivalent to 1, so we're using a double equals sign. And if a button press is detected, we're going to break the program, sending it right back to the beginning, where all 3 LEDs are off. And if the button hasn't been pressed, we can do the wig-wag loop by adding an else and indenting all subsequent lines. So if the button's pressed, we go back to the beginning, waiting for a push of the white button, or else just carry on with the loop. So now when we run the program, nothing happens until we press the white button. Then the amber warns that the gates are going to close. Then the 2 reds together, followed by the wig-wag, which will continue until our train has passed and the crossing is clear once again, when we can press the black button, which does need to be held down long enough for the program to cycle through at least one of those loops, which now I want to tweak a bit to speed up the flashing ever so slightly. Having written our program, we now need it to run automatically when our Pico's powered up away from the host. And to do that, I'm saving a copy, which I'm going to name as main.py. And even though my original version is still there on the Pico, that's the one it's going to run with our finished level crossing signs, the ones we made in part 1. We finished up that film, soldering the coloured extension wires to the stripboard base of the signs, and preparing the site on the level crossing, drilling through the baseboard, and clearing the foundations for the base, before threading the 4 wires down the hole. Exactly the same as what you'd do if you went for the shop-bought ones, rather than making your own. Then with the bases secure, at least for 2 of my signs, we can get on with wiring them up underneath the baseboard, which for my layout is a solid piece of MDF, into which I've cut a recess for another small piece of stripboard, which I want to label so I know which connector is which, the order actually matching what's going on top of the board. So now for a bit of soldering, starting with the wire for the left-hand red LED, the one I left a bit longer than the others, attaching it to the appropriate strip on the board. Then the same for the other 3, methodically working through the wires, stripping and soldering each one. Easy with my decoder wire, slightly more difficult with the enamelled coated stuff on the shop-bought signs. Then with one set done, it's on to the next. Again, starting with the slightly longer one, so we know our 2 signs are going to flash in unison and not be out of sync. With 2 out of my 4 signs wired up, let's get them connected to the controller. Eventually this is going to be mounted on the baseboard, but for now I'm going to use a piece of ribbon cable, snipping off the connectors at one end and soldering each wire to the stripboard, following my colour scheme reasonably closely, so I know which wire is which. Then flipping over the layout, I can plug them into the controller, pushing the 3 wires for the anodes into the same holes as the temporary LEDs, and the wire for the common cathode into a convenient ground pin on the Pico, which can be plugged into a USB power source, immediately launching the main.py program, ready for action. Now, if you've got a nice big permanent layout, you could fit the controller pretty much as it is onto your control panel, powered by a phone charger. But mine is far from permanent and short on space, so I found it a home on top of the board hidden by my signal box, the wires coming up from underneath. So instead of my chunky ribbon cable, I'm soldering some fine decoder wire, which will lie flat against the solid baseboard. The colour's pretty much the same as before, although my label will avoid confusion. And when all 4 are in place, I can thread them up through the hole I've drilled in the baseboard, which comes up underneath the signal box. Then with a little bit of dressing, just to make sure my wires don't get snagged, whenever the layout's moved, I can flip over the baseboard and deal with the top. This side of things has evolved quite a bit during the project, so what you're seeing here is very much the neat version. You'll recognise most of it, but I have sawn off the ends of the breadboard and importantly added the power supply, which now uses the columns at the end. To keep everything tidy, I've designed myself a tray, the exact size of the signal box, with a recess for the circuit board, all 3D printed on my far from fancy Ender 3. You can see I've left a lip for the walls of the signal box, which fits snugly on top. And I've got a hole in the corner, which is roughly in the same place as the hole through the baseboard, and it's through this I'm going to guide my wires, before pushing my tray into an area I've excavated through the foam board of my layout, fitting tight enough not to require any glue, although eventually my breadboard will need sticking down. You can ignore the bits of the power supply for now, We'll be coming to that very soon, but you'll notice it's using those 3 columns at the end of the board, where we had our resistors, so they've been moved and soldered directly to the ends of the wires, the final value being 460 ohms. And rather than using jumper cables, the resistors themselves push into the breadboard, alongside the pins on the Pico, the same ones as they were using before, the ends bent down so they fit in neatly. I've also put a bit of resistor wire on the end of the black cable, so it pushes in easily, next door to one of the ground pins. And that's our circuit, exactly the same as before, just a little bit neater. Now we come to the power supply, which I'm going to wire directly to the track, as my DCC layout has a constant AC voltage. But for the Pico I need DC, and only 5 volts, so I need a converter. I made something very similar for my network rail inspection train, to power its onboard Raspberry Pi Zero, streaming a driver's eye view of my layout, the video for which you can watch in the link above. And I'm going to borrow a bit of footage here to introduce how this works. We've actually got 2 jobs to do. First of all, we need to switch AC to DC, for which I'm using a bridge rectifier, essentially a bunch of diodes in a black plastic shell. And then we need a voltage regulator to drop the input to the 5 volts we need for the Pico. For the train I needed to make this as small as possible, building a little circuit board, wired to the pickups on the wheels of the Class 153, also recharging its onboard battery for a continuous power supply, so the Raspberry Pi is on all the time, even when the train isn't on the track. Our job here is rather more straightforward. I've got 2 wires soldered to the rails, which drop down through holes in the baseboard, reappearing with the others by the controller, and I've just added a little bit of wire with a bent end and some heat shrink insulation. As my layout is DCC, it uses alternating current, so now I want to fit my bridge rectifier to turn it into DC, and that's going to go in those 3 columns at the end of the breadboard, the negative and positive output pins plugging into diagonal opposites, where short jumpers will take them where they need to go. And I've shortened the legs, which need to be splayed a little to get over the central gap, so each has a separate connector. That orange wire is for the negative on the voltage regulator, and that and the brown one for the bridge rectifier connect to a ground pin on the Pico, leaving the 2 connectors on the other diagonal for the AC input from the track, our 2 grey wires, which can push into any of the holes in the column connected to the AC input, marked with the wavy line on the rectifier. And of course, as it's alternating current, it doesn't matter which one goes in which side, or which hole in the column it uses. So for the far side, I want to leave a bit of space, as that's where our regulator is going to go. So far, we've got the 2 alternating current inputs, and the negative DC output going to the ground pin on the Pico. And now we need to deal with the positive, the input for the voltage regulator, marked V in. Into that and the ground next door, I've soldered a simple 2-pin header, leaving V out clear. And these are going to push into holes in the breadboard for the V out of the rectifier and that orange wire which will go to ground. But before fitting, we need a connector for V out, a short jumper cable soldered to the terminal. We can't use the column on the breadboard, as that's already occupied by one of the AC inputs, so it's just V in and ground that push into the holes, with my blue wire reaching over the circuit and pushing into the 5-volt input on the Pico, the pin right at the end of the board. And that's our power supply. We've got the bridge rectifier converting AC to DC, and the regulator dropping the voltage to 5 volts for the Pico, so we can run the trains and power the controller, all with the same system. But if your layout is DC rather than digital, there's always the option of running on the USB, plugged into a phone charger. Now we come to the final bit of the film. With my controller hidden under the signal box, we can no longer get to the buttons, so I need to make a remote control, and then I'll be able to start and stop the sequence without lifting up any of the scenery. I'm using the same buttons or tactile switches that I used before, and I thought that orange and brown better reflected the colours of the lights when they're on and off, and I'm going to make a little circuit board for them, using another piece of strip board, just big enough to mount the 2 buttons. This time I can use all 4 legs, which I had to splay a little to get through the holes, pushing them through what I think of as the back of the board, so we can solder them to the copper strips on the other side, making sure we've got the connected pairs on the same strip, and then solder some wires, white for the start button and a grey one for stop. I'm using the outer row of the strip board for each, so the centre ones can be used for the common positive and soldered together to a single blue wire. Then all 3 can be fed through a hole I've drilled in the board, making sure they don't get tangled up. And when they're all the way through, I can lower my button board into a rectangle I've cut in the scenery. Eventually, this can be disguised with some trackside kit. The other ends come up through the hole under my controller. Once again, I've added some bent wire and some heat shrink, and these are going to go in the same columns as the other buttons, connecting to the same pins on the Pico, so our program doesn't need to change. Then the same with the wire for the stop button, next door to pin 27, and then the blue for the common positive, which can actually go into any of the holes on the outer row, where it'll connect to the 3V output of the Pico, just like the white and black buttons, which we can still use if we want. Then time to power up my layout, connecting the output from my Hornby Select and switching on, powering up the Pico and launching main.py, where we can start and stop the lighting sequence, either using the buttons on the controller or the much more convenient remote control, which itself could be replaced by some automated system triggered by a passing train, all of which we could add to our controller, adapting the existing software to accommodate any sensors we require. But that will very much have to wait for another video. So for now, it's on with the signal box, and a press of the orange button at the sound of an approaching train, triggering the light sequence, giving any motorist plenty of time to clear the crossing, no matter what's coming round the corner.